Okay, well, welcome back, both of you. We're gonna have a full class today, huh? Um, it's gonna be a short one today. Let me share with you just to make sure, and I'll send an email as a reminder for everyone, but today is the 22nd, obviously, right? So today I'll finish this up, finish chapter 14. Where it is? There it is. Today's 22nd. Okay, we're not gonna have anything this Thursday. It's Thanksgiving. So we come back on the 29th. So today I'll finish up chapter 14. Only about 6, 7 slides left. We'll finish up early today. And then next, when you come back on the 6th, on the 29th, we'll do chapter 15, the last chapter, which also is very short, maybe 8, 9 slides. We'll get that knocked out. And then, so that means that Thursday, okay, and the next, so Thursday the 1st, the 6th, and the 8th will be another study day, self-study day scenario for you. And then I will be here on the 13th for a time period. I haven't decided how much time, but in case there is questions about the final on the 13th, I'll be here. I'll be available for you again on Zoom. And the 13th is the last day for everything. So if you have anything that is you want to go back and do, the activities or anything you missed, the homework, you can still do it. Also, a reminder about the homework. If you only did one attempt and you go back to do the second attempt, and if you did it when it was due or before the due date, and you do the second attempt and you get a better grade, Canvas, because it thinks it's after the due date, will treat it late. But I will go in there and remove the penalty if you actually did the original attempt when it was due, okay, to get you the higher grade. Other than that, that's our schedule. We're gonna have a lot of self-study days here. I'm available to help you get ready for the final. There is on the course website also in the module a final exam example that you can use for a resource to help you study. It's going to cover all the chapters. Okay, it's 110 minutes, all multiple choice. Approximately, I don't know, 3 to 4 questions per chapter. Okay, questions will be very similar to what you've seen before. I'm also going to try to find out if I can open up the exams we did already for you to go back and review with the correct answers. That's a departmental thing, so let me find out. I will send email to that effect and possibly have it open up certain time, maybe the week of the 5th, to give you time to go back in and take a look at the ones you missed and get the correct answer. But I got to get the okay from the department to do that. Okay, any questions? Yeah, well, let us finish up where we ended up, and then we'll call it a day. All right, so we have been talking about the last three visits here, talking about intermolecular forces, okay? And to rehash a little bit is we first have to take the molecule and define its polarity and whether that compound is polar, nonpolar, ionic, and aqueous system defines what type of intermolecular force we assign to it. Once we do that, and we know the strength of the intermolecular force, we can do a compare and contrast between two compounds. As I stated before, we cannot do an exact comparison with respect to the physical properties. Well, that's what we're going to compare: physical properties, specific boiling point, vapor pressure, surface tension, and viscosity. We can't determine the absolute values, but we could do relative. Who's going to have the higher boiling point, who has the less boiling point, things like that. All based on the intermolecular forces that these molecules undergo. And keep in mind that these intermolecular forces, these are these forces of molecules interacting with other molecules. Okay. And sometimes that interaction is very strong, and sometimes it's not as strong. So it doesn't take much energy to break up those intermolecular forces. So that in effect affects their physical property of boiling point, melting point, affects all kinds of physical properties. Okay. So we have an example here, and it's a typical type of question we're asking. Let's compare ammonia and fluorine. And to do that, we gotta know the polarity of it, right? And so this is all tied into the Lewis-Strauss structures if we need it. So you need to know whether that compound is polar or non-polar. Well, if we look at fluorine, okay, fluorine is the diatomic. Oh, excuse me, let's clear this up here. I was writing iodine. I don't know why I had iodine in the brain. Fluorine is diatomic, okay? And so essentially we have two molecules. This is the Lewis-Strauss structure for it. You can go and verify that if you like. But being diatomic, two atoms are the same. Therefore, the electronegativity are equal. Therefore, there's no pull with respect to the bond that they are sharing. So it's equal pulling, resulting in a non-polar covalent bond. Okay, non-polar covalent bond. If you recall, all diatomics, all 7 of them, are non-polar covalent bonds, including the carbon-hydrogen bond. Okay, non-polar covalent bonds. Ammonia is the other species, which has the formula of NH3. We've been using this quite often, so you just might want to just put that guy in long-term memory. And all right, but if you forgot if it's whether it's polar or not, when you do the Lewis-Strauss structure, nitrogen is the central atom. So go through the process of figuring out the Lewis-Strauss structure, okay? And we end up with a lone pair on the central atom. And so this general formula is the AB3E. The fact we got a lone pair in the central atom, as I stated before, automatically you have a polar covalent, polar compound, okay? And this is now is polar because we have polar covalent bonds here, okay? Oh, got one more. Now, once we know the type of compound it is, we can now assign the IMF. Well, the IMF for nonpolar compounds is the London dispersion forces, okay? All nonpolar species, all nonpolar compounds, the only force they have is the London dispersion forces, okay? Even those compounds that have polar bonds, but their polar bonds cancel out. They cancel each other out. So the net effect makes it into a nonpolar species or compound, just like carbon dioxide. Okay, we went at length with that. Ammonia is polar. And so we can either think, now there's no mention here of ions, so we can eliminate completely the ion dipole force. We've got no ion dipole force here, okay? So you either left with London dispersion forces, dipole, or hydrogen bridging. So either dipole or hydrogen bridging force. Well, and remember the hydrogen bridging force deals with hydrogens that are bonded to nitrogen or oxygen or fluoride. And we have nitrogen bonded to hydrogen. So that means that the force involved here is hydrogen bridging force. Yes, it is a dipole. The nitrogen-hydrogen bond is a dipole, okay? But it's a dipole force in itself, in its own category, because the strength involved in that interaction. And so it's elevated to what is called a hydrogen bridging force, okay? And that's something that I want to make clear between dipole and hydrogen bridging force. Both of them obviously are a dipole interaction. We end up with a dipole on that bond. There's a partial positive side and a partial negative side. And so the hydrogen nitrogen bond is a dipole, but because the nature of the beast is an elevated dipole interaction, and it's specifically called hydrogen bridging force. Or you may hear the term hydrogen bonding. We try to stay away from that term because it infers that there's an actual bond, and it's not the case. It's an interaction. All right, so what we've done here so far is we look at the molecules we're given, looked at the structure, determine what type of compound it is, and from that, polar, nonpolar, and from that information, determine what type of IMF to give it. We assign for fluorine the London dispersion forces, and for ammonia, the hydrogen bridging force. Okay. So let's clear my mess here. All right. So there's the formula. That's the IMF assigned to it, okay, because it's a non-polar species. And then ammonia is the hydrogen bridging force. Okay, now questions that can come up. Question number 1 says, well, of these two, which has the stronger IMF? Well, we talked about this with respect to IMF. The London dispersion forces were the weakest ones compared to the hydrogen bridging force, which are the stronger ones. And then the dipole force was somewhere in between. And so in this case, ammonia has the stronger force. Keeping in mind, as you determine this, having the stronger force is going to require more energy to break up that interaction between the molecules, okay? Now, which has the lower boiling point? Okay, so the lower boiling point means that when we look at species, I'm just going to generally draw them as two spheres, which could represent, the fluorine or the ammonia molecule, that's whichever. But we're looking at that force between them, okay? And so if that force is strong, and then it's going to require a lot of energy to break up that interaction between these two species, these two molecules. If it's not as strong, then it's going to take lower force to break it. And so in this scenario, fluorine would have the lower boiling point because it has the weakest force, which is the London force. And it doesn't take a lot of energy for it to break up the interaction between the molecules. Okay, so maybe if I would, let me do this. And so what we have is fluorine here interacting with another molecule of fluorine. And then we have ammonia here interacting with another molecule of ammonia. Okay, not the scale. So, but we're looking at that force to break up that interaction. Okay, so third question, which is polar? Okay, we answered that in the beginning because we know that ammonia is polar, it has polar bonds. And so ammonia is polar species, whereas all diatomic molecules are nonpolar. Okay. Which has a higher vapor pressure. Remember that the vapor pressure is the measure of pressure in a closed container, okay? And so if we look at the interaction in the liquid phase, if that interaction is weak, then more molecules would be going from the liquid into the gas phase, okay? So like a closed soda pop. More material goes into the gas phase if the intermolecular force is weak. So in this case, the one with the weaker force would be fluorine. They will have a higher vapor pressure than ammonia. Okay, and then if these were liquids, which would be the least viscous. Okay. So in this case, again, the least viscous would be fluorine because it has the weaker intermolecular forces. Then with respect to surface tension, the one with the stronger intermolecular force would have the more or the greater surface tension. So that's what we're doing here. Again, based on the structure of the molecule gives us the polarity of the molecule. From the polarity of the molecule, we assign the intermolecular force. And from that information, then we can do a compare and contrast, okay? And compare and contrast. Now, I was asked a question once, well, what if you had two species that both have hydrogen bridging force, okay? Or they both have London forces, okay? How can you compare and contrast? Well, you can, you still can. It's that what you think about is who's the bigger molecule. And so fluorine, for example, will have London forces, but a hydrocarbon would also have London forces. But if the hydrocarbon is humongous, then it would have a lot more London force than, say, something as small as fluorine. So the size of the molecule within the force plays a factor. So you can still do a compare and contrast within the force that you are looking at two molecules with the same force. You ask the question, well, who's bigger? Because whoever's bigger would have a lot more electrons, because all this is related to electrons and the outermost shell in the valence electrons, okay? These valence electrons are playing havoc on the properties of chemicals. They define what is happening out there, why certain molecules at certain temperatures behave, are either solid or liquid or even gas, okay? All right, let's clear this up. All right, so to summarize all this, we can say the following: that as the intermolecular force increases, then the viscosity increases, okay? As it gets stronger, as the force gets stronger, we're going to make a more viscous material. And so we can deduce backwards without, you know, we can say in that example of, say, honey and water. Well, we know that honey is very viscous and oil is very, well, thick oil, very viscous compared to water, right? Some heavyweight oil. And so we can say that the intermolecular forces of honey and oil is greater than, say, water, because those species are more viscous and flow slowly. The boiling point increases, okay? Again, is we compare, you know, London forces to hydrogen bridging force. Hydrogen bridging forces are stronger. They're going to require more energy to break up the interaction. So the boiling point increases, which along with the surface tension, which causes the liquids to beat up more so because the molecules, again, are holding on to each other with a greater force, okay? But the vapor pressure decreases. Because the molecules are being held on with a greater force, in the liquid phase, there's going to be less of them going into the gas phase, and hence the pressure, vapor pressure decreases. All right. So this type of question could be readily reversed and say, as azimuth decreases, then, then viscosity decreases, boiling point, et cetera, et cetera. Okay. So be aware these type of questions can be asked in a number of ways. All right, so the structure of water, we're not going to say much about water. Water is very unique. We're finding out even to this day, water is being researched. There's a lot of information. It has very unique properties. It's very unique. I just saw a video the other day with a summary of water and the properties. And I guess one of the debates about two different types of water with different densities, all related to the intermolecular force that's involved here, these molecules. Very fascinating work. And then having to do with something that's beyond the scope 130 of quantum mechanics. But anyway, water is very, very unique. The structure has two bonding electrons, two lone pair non-bonding electrons. We talked about this when we did Lewis-Dot structure. The molecular geometry has a bond angle of less than 109.5. Recall that 109.5 was kind of our benchmark with all the molecules in the central atom. 4 molecules wrapped bonded to a central atom resulted in a 109.5 bond angle. Okay. So, and because of the lone pairs, that bond angle gets squished down. And since water has 2 lone pairs, that bond angle gets much, much less than 109.5. Water is very polar, extremely polar, and will dissolve many. In fact, it will dissolve anything with time. It's a relative. Some things it dissolves immediately, and certain things, take some time period, but eventually they go in solution. Okay, because water is that way. It will dissolve everything. Okay, water is very strong hydrogen bridging. We talked about that. Okay. Oh, number 1 back to number 1. One thing to remember about polarity, that polar substances will dissolve polar substances. Like dissolves like. We all know that you can't mix oil and water, okay? Case in point, look at Italian dressing. You have 2 layers. You have an aqueous layer and an oil layer, okay? So oil is nonpolar. Water, aqueous, is polar. Those 2 are not mixed. Okay? So like dissolves like. Remember that. We're going to talk about that next chapter. Some properties of water, very polar, as I stated, very high IMF, hydrogen bridging, low vapor pressure, boiling point 100 degrees Celsius with the melting point to 0 degrees Celsius, quite a range there. High surface tension, and very unique is that most liquids, it doesn't happen to most liquids, that water expands as it freezes, and it has to do with the crystalline structure that it forms. A lot to do with the intermolecular forces of the atoms involved within water. But density of ice is much less than the density of water itself. Very interesting. A lot of stuff going on. Here's the structure of ice on the far left. Everything all lines up, very ordered, and then a little snowflake on the right, which I'm told everyone's unique. Every snowflake's unique. I don't know that for sure. No, I'll go with that's what they tell us. All right, so it brings us to this heating curve, okay, which is basically any solid material that we can take, and what we do is the following: is we take the solid material. We have a graph here of temperature, okay, and the amount of energy heated to the system. Okay, my graphing here is not to scale, but assume it is. Okay, and so what we do is we put heat energy into the system, and we notice temperature. We have these dots of data dots. We can collect this graph and make this graph. All right. Notice that the result is there is a plateau that is generated. First plateau where the solid begins to change from a solid to a liquid. Then there's a very sharp increase in temperature. Note the temperature over here, boiling point increase. And then we hit a second plateau, okay, to eventually all the liquid material is converted and it shoots, temperature goes up again, a sharp increase to almost to infinity here. And everything gets converted from a solid to liquid to gas. What's interesting here are these two plateaus, okay? I'm going to talk about that for a second. Next one. So let's take, for example, we can use water, okay, as an example. So if we take ice, here's a solid form, and we put energy into the system, okay, put energy into the system, and we're going to end up with this particular graph, and we collect the data. So we put in X amount of energy, note the temperature, and we collect this data. So obviously the ice cube here, temperature starts to go up. Now, in this rise, the water is in the solid phase completely until it hits the first plateau, which, by the way, happens to be at 0 degrees. So we're using H2O as an example, but this can be most any material, okay? So at this point, there is a plateau. And at that plateau, the solid that's been, you start off with, is now being converted to liquid. No, regardless of how much energy you put into the system, that temperature remains constant. So what is happening here is as you're putting energy into the system, all of that energy that you put into the system is used to break up that intermolecular force between the molecules, whatever these molecules are, okay? Is breaking up this intermolecular force. And hence, instead of the temperature going up, temperature remains constant until such time that all of the solid has been converted to liquid. And then we find our second rise again up to, guess what? Another plateau. And also lies in the case of going from solid to liquid, the second plateau is where the liquid is being converted to gas. So again, we put in energy into the system, we're breaking up the intermolecular forces and driving the molecules further apart until such time that all of the liquid has been converted to gas and temperature goes up again, okay? And so at the rises, is the actual phase. So all that rises, all solid, liquid, and gas respectively. At the plateaus, that is where the physical state is being converted from one physical state to the other, okay? And the temperature remains constant. So, FYI for little note at home, when you boil water and you're making some spaghetti at home, once you got the water boiling, you might be tempted to kick up the temperature. You're wasting your energy. Why? Because you're at that plateau here, okay? That no matter how much energy you put in, you can put a flamethrower on your pot and put a lot more energy. All you're gonna do is that liquid is, if you're at this point right here, that liquid is just gonna absorb it until all of that liquid has been converted to gas. So save your energy. Once you're boiled, turn the heat down, and let it simmer and boil on, with less amount of energy. All right, so at these plateaus, what is happening here is, again, all the energy that you put into the system. Here, somebody has a question. Yeah, no worries, Kat. all the energy that you put into the system is being utilized to convert it, to break up the molecules, to break up the intermolecular forces that are occurring between the molecules, and push it into the next phase. Okay, so during the phase changes, temperatures remain constant. All the energy goes into breaking the intermolecular forces. I can't overemphasize that. Please don't tell me they're breaking bonds. We're not breaking bonds here, okay? We are breaking the intermolecular forces. Bonds energy takes a lot more energy than what you're doing when just boiling water, for example. You're breaking the intermolecular forces, okay? Not bonds. All right. I told you today would be short and sweet. Congratulations. You're almost done with this chapter, this semester here. All right, so that's chapter 14, the end of it, dealing with intermolecular forces. Took a little bit longer than normal, that's okay. And like I stated earlier, I know Kate, you came in late, but I was gonna just finish up 14. And then next Tuesday, we'll do 15 and you're done for the semester, because 15 is also a short one. All right, and then the following Tuesday, we'll probably do another self-study day. So, start getting ready for the final. Use the